Hello, this is 3.9, Antiderivatives, first section in Unit 4 for us. And so they start the antiderivatives in Chapter 3, but they continue the antiderivatives all the way through Chapter 4 and also through Chapter 5. So here they tell us the definition of the antiderivative. They say a function f is an antiderivative of lowercase f. So they're calling the antiderivative capital F of lowercase f on a interval I, provided that when you take the derivative of f, that you get lowercase f. So when you take the derivative of this function, you get back the function for all x in the interval I. And then they're asking us here to find the most general antiderivative of the function. Check your answer by differentiation. Why can't I say that today? By finding the derivative. And so we'll give a check to it and make sure that it works. And so we're saying that we're going to find the antiderivative of f, lowercase f, and they called that capital F. And so notation, I'm taking the antiderivative of lowercase f, and they're calling that answer capital F. And then now I'm going to find the antiderivative of x squared. So I'm thinking to myself, what, when I take the derivative of it, do I get x squared? So that's what I'm trying to think and trying to piece it together. You probably remember when you take the derivative of something that you take away 1 from the exponent. So it might make sense that, that it would be something that had x to the third in it, because you would take away 1 from the exponent. So if you kind of imagine when you take the derivative, so if you kind of imagine taking the derivative of this, well, the 3 would come down in front, and then I would take away 1 from the exponent, which definitely gives me x to the second. But I want the answer to totally be x to the second. So what do you think I have to have? I got to divide by 3. And so if I divide by 3, now when I find the derivative of this, the 3 comes down in front, cancels with the 3 in the denominator. Take away 1 from the exponent, I get x to the second. The 3 right here is a constant. It just holds still. And I kind of imagine that same story. If I take, when I take the derivative of it, I get x to the first, right? And so if you kind of sit there and you start thinking about it, well, you'd have to add 1 to the exponent. The exponent is 1, and if I add 1, I get x to the second. And then now if you imagine taking the derivative, the 2 would come down in front. It would multiply with the 3. I want the 3 there. And so if you're saying, hey, you got to divide by 2, you're right. He hasn't told us any rules yet. He's just having us go on our own and try to figure it out, right? And so when you take the derivative of something, you get 2. Can you think of what that might be? So I hope that you're thinking about it, and I hope you're saying 2x. So that when I take the derivative of 2x, I get 2. And you might be thinking, am I all done? And how you could check your answer is by finding the derivative, right? And so if I try to check my answer, then what I'm going to do is I'm going to find the derivative and then see if I get back what we started with. So this is me saying to myself, hey, let me check this answer. So they said that when you take the derivative of f, this would be f prime at x, they said that they were going to call that little f. Okay. And then when I take the derivative here, the 3 comes down in front, raised to the second. The 3 was a constant in the denominator, so the 3's cancel. X squared. The minus 3 halves is a constant, so you take the 2x when you take the derivative. The 2's cancel and give me minus 3x. So I'm kind of checking, hey, is this giving me back what I started with? And then I take the derivative of 2x and I get 2. And so definitely the plus 2 comes down. Now, one other thing that I could have had here, y'all agree with me? I could have had plus 7. And then when you take the derivative of it, you would get 0. So you wouldn't know. Or it could have been plus 10. right? And you take the derivative of 10 and you would get back here, right there. You wouldn't know what you had. Well, that's called a constant. So I'm going to add right here a constant. I could have any constant there. And so this here is my antiderivative, the most general antiderivative, so that when I take the derivative of the constant, I get 0. Right? And so I wouldn't have that written. This was me just checking it by finding the derivative to make sure it works. Then what they're saying is that you kind of have a whole family of antiderivatives depending on what your C was. And they named them here C1, C2, C3, C4. So they're saying capital F. And then that value C, it could have been 10, or it could have been 7, or it could have been negative 53, it could have been whatever. They're actually going to give us a way of finding that value C for some functions. And then you get this whole family of antiderivatives. And what do we know about that whole family of antiderivatives is that since they're just varying by a constant, they would just be the same exact shape of the function, just up or down. And so anyway, so that's all that it's showing you. So now they kind of let us try to figure that out on our own, and we did. We did a lovely job at that. And then now they're going to giving us some rules here. And they're saying if we had f at x equals x to the n, where n's not equal to -1, then the antiderivative, remember they said that the antiderivative of lowercase f, they were going to call that capital F. And then you probably noticed we figured that out, that you had to add 1 to the exponent. So you add 1 to the exponent and you divide by the same darn thing. And then plus a constant C. Now, I want you to notice that even though I took the antiderivative here, I took the antiderivative there, I took the antiderivative there, I didn't write, plus C for each and every one of them, because each of them could have had a constant. It's true, but you could add those constants up, all of them together, they're all constants, and call it a super constant is the idea. And so you only have that only just the one time. Now, the other thing that they told us, and we figured this out too, is that if you are, so there's have some function and you have C times your function, well, the C just holds still. And then you take the antiderivative of the function. And we certainly did that here too, right? We said that the 3 was just going to hold still. So I wrote the 3 down, and then I said, okay, now we're going to take the derivative of x, right? So we had the coefficient C, and which the coefficient there, our constant, which was -3, and then we just took the antiderivative of x, which was x to the second over 2. And so, yeah, so certainly that's true. And so, and then the other one that we used here as well, which is that if you have a string of adds and subtracts, and you're trying to take the antiderivative of the pieces, you just take the antiderivative of that piece, plus or minus whichever it is, the antiderivative of the next piece, plus or minus whatever it is, and then at the end, you just add one super constant on there. And so that's what this is saying. So the antiderivative of G is capital G. The antiderivative of H is capital H. And it's just saying, just take the antiderivative of the pieces is all that it's saying. So we actually did that when we figured this one out, when we were just guessing at it. And now they're just saying, here is some formulas that you can use, that constants hold still, and the unpower rule, as I call it, where you add 1 and divide by the same darn thing. Okay, so we're going to see what we have. Was that a problem out of your book? Yeah, that was problem number 6 out of your book. This is problem 10 out of your book. So problem 10 out of your book. And so as I go looking at problem 10 here, to find the antiderivative, all I really have is the unpower rule. They call it in your book the power rule, but I like to call it the unpower rule since I feel like I'm going backwards and finding the antiderivative. So either way, though, and so they don't have what to do if you have something like x minus 5 quantity squared. And so they don't tell us what to do about that situation. And I want to find the antiderivative of that. And so some of you might have the idea that, well, why don't you just multiply it together and it'll be something just like what you took the antiderivative of just a few minutes ago, and you can just go do the pieces. So this is actually when you have that whole thing quantity squared is actually a multiply is what it is. It's x minus 5 times x minus 5. And I can't do the antiderivative of a multiply quite yet. And so the idea is, well, just multiply it together. So when I do that, so I'm not finding the antiderivative yet. I'm just foiling this together so that I can make it to be something that I can find the antiderivative of. You'll learn some rules that'll make you forget that this was just the easiest way of finding the antiderivative of this is just to FOIL it. I'm telling you, it'll happen. You'll get where you're thinking, I got to make it more complicated than that. So I got 10 in the center, negative 10 in the center. So I have not found the antiderivative yet. And I'm going to now. I'm going to find the antiderivative now. So I've got it now where I've got these three pieces, and I can use the add subtract rule, which means find the antiderivative of each piece. And so the antiderivative of lowercase f, they said that they were going to call it capital F. And so we're going to do that same thing. If you're thinking that's kind of awkward notation, when you find the antiderivative of it, to call it capital F, I'm with you. And they're going to give it better notation in chapter 4. But that's the notation they give right here in chapter 3.9. And then I'm going to find the antiderivative of this. Well, we have the unpower rule, which says add 1 to the exponent. So 2 plus 1 is 3. And then divide by the same darn thing. Minus the 10 holds still times add 1 to the exponent, x to the second, and divide by the same darn thing. Plus, and then the antiderivative of 25 is just simply 25x, so plus 25x. So that when I take the derivative of it, I get 25, right? Plus a constant. And notice I just put one constant even though I took the antiderivative of 3 different things. And now I'm going to clean it up. And yeah, you get where you can clean it up in your head as you go along. But I'm pretending like right now that I'm cleaning it up afterward and not doing it in my head so that everyone can see that, hey, you just use those properties, right? And so the 3 properties that we had, in fact, we used all 3 of them that time, right? We used the power rule. I don't have that underneath the page, where we added 1 to the exponent and divided by the same darn thing. We put the constant out in the front and then found the antiderivative of the function. And we had a string of adds and subtracts, and we just found the antiderivative of each piece. Okay. So this one is a division, and you notice we don't have a rule for division. And the book gets a little funky here, I have to admit. And they say that, hey, the denominator right here, before I do anything else, should not be 0. I have G, and G has domain issues. The only thing that wouldn't be okay for values of x would be for x to be 0. So x equaling to 0 should not be okay. And so I'm going to just write that right there and kind of hold on to that. If I want to find the antiderivative here, then what I'm going to do is I don't know how to find the antiderivative of a division, right? I know how to find the antiderivative of a string of adds and subtracts, though. And so since this is a monomial in the denominator, I can divide the pieces. So this is going to be, I have not found the antiderivative yet. I wish I would have given myself a little more room. But this is going to be 5x to the 6th minus 4x to the 3rd over x to the 6th, right? Divide the pieces, plus 2x to the 6th over x to the 6th. And very soon, you'll see that, okay, I want to write it so that I can use the unpower rule. So just like I did, so this is 5x to the negative 6. So this is 3 take away 6 is 3. So this is minus 4x to the negative 3rd. And then x to the 6 divided by x to the 6 is 2. I have not found the antiderivative yet, but I'm going to kind of draw a line and I'm going to go find the antiderivative. So the antiderivative of g is g at x. You add 1 to the exponent. So when I add 1 to negative 6, that makes negative 5. So the 5 holds still, right? and I put my finger over it, and I say I'm going to take the antiderivative of x to the negative 6 using the unpower rule, as I call it. And so add 1, which would be x to the fifth, negative fifth, and divide by the same darn thing, which is negative fifth. Minus 4, hold still, add 1. So when I add 1, negative 3 plus 1 is negative 2. And then divide by the same darn thing. And then plus 2x, right, plus a constant. And then cleaning this up just a little bit, the 5 and the 5 cancel. So this becomes our antiderivative equals negative x to the negative fifth. A negative and a negative is a positive, and 2 and 4 make 2, x to the negative 2, plus 2x plus c. And I guess if I wanted to, I could write that as x to the 1 over 5. X, no, that's not how you say that. 1 divided by x to the fifth, and 2 divided by x to the second. I could do that, and it's not necessary. But this is where the book is just a little bit awkward, and then doesn't do it consistently. So if they did it consistently, but I want you to see so that if you go do any problems in the book, if you go do any of the homework problems, now you might be saying, oh, is there homework problems in the book that I can do? Yes, there is. And there are answers to them too. I have them right on the first page here, 3.9. And my recommendation is to do half of them and then come back and see if you can do the other half at a later time. Or do a third of them and come back and do another third of them and then another third of them if you like. But what they do in the book here is they said because x shouldn't be equal to 0, they say that, hey, this could be really piecewise defined. And so they write this as g at x, which is our derivative, equals, and then they say, we're going to let x be greater than, oh, I'm not going to have enough room if I'm not careful here. Sorry, I'm going to scoot over. This is if x is greater than 0. And then they put the same darn derivative here that we already found. And they say plus C1. And then they say, well, what if it is smaller than 0? Well, the same darn derivative, but then if it was smaller than 0, it's possible that it could have a different constant. So they say plus C2 if x is less than 0. And then they do that on this problem, and that's what they have kind of in the back of the book. And then they'll have another one where they do the same thing because it had domain issues, and then they'll have another one where they don't address them at all. And it's almost like the person who's solving it didn't kind of worry about it. I probably could have said, let me go and carefully look in the back of the book and ignore the situation where you have these domain issues, except for you're going to see it in Calc 2. And so he has this is from the 8th edition of the Stewart book on page 331. He has a similar example in the 9th edition. They actually changed it. Instead of being 1 over x squared, they changed it to be 1 over 2x to the third instead. And so, but go through the whole example, kind of explaining to you, about, hey, the denominator shouldn't equal 0. So it really, this is what we're having here, but really it should be when we find the antiderivative of that, because it could have different constants, right? So they said that it could, depending on if it's bigger than or smaller than 0. And so they kind of did just what I've done here. I guess I said bigger than 0 goes with C1, but it matters not, right? I mean, that's constant, so it doesn't matter at all. I was going to go and pick up from the 9th edition and put it right there because that's the book we're using. And of course, this is the last time, and I couldn't get the book up in order to do that. So I just had to say, well, you can go and look in your book if you want at the example they have, but it has that same idea. Okay. And so do you need to worry about this, I guess, is only for looking in the back of the book and seeing the answer. And so for right now, we're not going to worry about that. And in fact, I'll avoid the situation entirely is what I'll do. Okay, this is problem 23. they're asking me to find the most general antiderivative of the function. And I notice I've got the cube root. And so what you want to do is you want to write that with, instead of with the cube root notation, you want to write that as v to the 2/3 so that you can use your n power rule. And so I'm not finding the derivative yet. Oh, I was going to use that pencil. I'm not finding, I don't know that it matters, but I don't know why, but I had found this pencil and was so darn excited about it, and then started using that other pencil. So I'm just writing it so that I can find the antiderivative. And I'm thinking to myself, I know the constant 3 will just hold still, and then I want to take the antiderivative of secant squared. So can you think of something that when you find the derivative of it, you get secant squared? Because I know this one here, add 1 and divide by the same darn thing, right? That's going to be kind of the story on there. And I'm going to show you a shortcut on it, definitely, that I use. So I hope that I've chit-chatted enough that you're in your memory are saying, yes, when you take the derivative of tangent v, you get secant squared v. I'm hoping that's what you're saying, so that if you're doing the antiderivative, you would be getting tangent v here. So here, the antiderivative lowercase is uppercase, they say. So now I am going to find the antiderivative, right? I'll even write on this line, antiderivative. That's what I'm doing now. I just made the line on the others, not thinking maybe I should make a note of what I'm going to do next. But I made the line on the others just saying that, hey, I got it cleaned up, and now I'm going to find the antiderivative. So you add 1. Oh, I put at x, but it's v. At v. So I add 1. So I'm thinking 2/3 plus 1, right? That's what I'm thinking, because I'm going to add 1 to the exponent. And that equals 5/3. And you can use your calculator. And so this is going to look like v to the 5/3 divided by the same darn thing, plus 3. And then the antiderivative of secant squared v, which is tangent of v, plus a constant. And that's not simplified to write divided by 5/3. And so I just need to fix that up. And so this is kind of what I have, right? I have divided by, can you see what I'm writing? Yes, 5/3. That's what I have, right? And that's the same as multiplying by 3/5. So I have to admit that I don't normally write it like I wrote it here. Instead of writing divided by 5/3, I tell myself that when it's a fraction, that I'm going to multiply by the reciprocal. And so this would be 3/5 times v to the 5/3 plus 3 tangent of v plus c. And there's our most general antiderivative. Tell you what, I got some situations going on here at my house. I got a big old spider right there. Looks like a nice spider, though. I can't move the camera over there so that you can see it, but I got a spider who's sit down beside her, and then I got all these hummingbirds coming and talking to me at my window. I don't know if it's because they're dissatisfied with what I've got out there in their hummingbird feeder or what is going on. Okay, and then some basic trig antiderivatives, and they're important to know. And this is how I have them memorized. I know that the Stewart book doesn't necessarily have you memorize them this way, but he does actually ask you questions that use this. And so so this is a bit of, if you had the chain rule in there, how you can undo it, because if you were going to take the derivative of that, remember that's how you would check it, because you have ax, you would have chain rule, and that would be times an a, and then the a's would cancel when you divide by the a. So that's the reason that they put in the a. I think it's kind of nice to kind of have it as that is your way of memorizing it. If that's not how you want to memorize it, you don't have to. And so you can just take your white out and move the a out, and put the a out and put the a out right there. Just white them all out, make them one is what you would do, and that would give you them without the a in there. I think it's kind of helpful to have the a in there because we're going to, when we have ones that we're trying to find the antiderivative, it's a real time saver to know that if it has just a coefficient, all you do is divide by that coefficient. I think it is anyway. Anyway, so uh, when you take the antiderivative of sine, you get negative cosine. You take the antiderivative of cosine, you get positive sine. And yes, that's backwards from the derivative. You take the antiderivative of secant squared, you get tangent, right? Take the antiderivative of secant square, cosecant squared of some input, you get the negative cotangent. Take the antiderivative of secant and at the same angle, times tangent of the same angle, you get the secant of a over x plus c. And the cosecant times the cotangent, you get this. So I don't have these antiderivatives necessarily memorized. I have to admit I have this side memorized, right? I say to myself, if I was to take the derivative of negative cosine, what would I get? Well, I get positive sine, etc. And then there's some trig that you learned in Math 1 or wherever you learned it, wherever you learned your trig. And so for me, it was in the intermediate algebra classes where I learned the non-existent trig that I learned. I didn't learn very much trig. I wish I would have learned more. But these are some identities that come up in Calc 1 all the time. There's 9 of them that come up in Calc 1 all the time, and I bet you know some of them already, and that you learned them in the trig class or wherever you learned them. And but they come up all the time. They're going to add a whole bunch more to this list that come up all the time in Calc 2. And so I'll just put the ones out there that we use, the ones that, that seem to come up for us. So that cosine squared x equals 1/2 times 1 plus cosine of 2x. And sine squared x equals 1/2 1 minus cosine 2x. And sine of 2x equals 2 sine of x cosine of x. This is the Pythagorean identity that sine squared x plus cosine squared x equals 1. This is a rearrangement of that same Pythagorean identity, only just dividing here every single one of the pieces by sine squared, right? Imagine if you divided by sine squared divided by sine squared is 1. And then cosine squared divided by sine squared is equal to cotangent squared. Whoops, I was getting this one right here, wasn't I? Cotangent squared. And then 1 divided by sine squared is equal to cosecant squared. If I wanted this one, what am I going to have to divide every piece by? So I hope you're saying cosine squared. So sine squared divided by cosine squared is tangent squared. There it is. Cosine squared divided by cosine squared is 1. There it is. And 1 divided by cosine squared is secant squared. So yes, that if you know this one and know that all you have to do is divide by sine squared or cosine squared, you get the other two for free. And they're all called Pythagorean identities. And then secant x equals 1 divided by cosine of x. I'm sure you know that. And actually, we used that upstairs, didn't we? Just a second ago. And cosecant of x is equal to 1 over sine of x. And cotangent of x is equal to 1 over tangent of x, or equal to cosine of x divided by sine of x. So those are the 9 that we need in this class. And we also need to know these. And if you like, you can know them without the a, if you like, or you can know them with the a. I like to know them with the a. That's just me. And so either way, it's all good. Okay. So this one right here is asking us to find the most general antiderivative of the function. And all we would have to do if we have it memorized, right, is they're trying to get me to find the antiderivative of sine of 3x in this case. So I'm over here looking. Okay, here's my sine of 3x, ax. The antiderivative is negative cosine. Right? So I'm going to find the antiderivative, negative cosine of 3x, that same angle, divided by a, which was 3 in this case, plus the constant c. So if I take the antiderivative of f, I get capital F, right? That's the convention that they are teaching us right now, and they're going to show us something different in a few minutes. And then how can I check this answer? Well, I could find the derivative of it. So if I find the derivative of f, I get f prime, which they define to be lowercase f, right? And then if I take the derivative of this, the derivative, I'm going to have to use the chain rule, right? The negative 1/3 just holds still. So I'll put my finger on it. Use the chain rule to take the derivative of that. Well, you get, when you take the derivative, you get negative sine of 3x times the inside, which is 3, which is going to cancel with that 3. The negative will cancel with that negative, making that plus a constant, and the derivative of a constant is 0. Okay, so we did a lovely job on it. And then there's some initial value problems. Quack, quack, quack goes my phone. And so I will make my quacker turn off. Okay, so here it says, use a particular solution to find C. These are called initial value problems. An equation that involves derivatives is called a differential equation. So that's one thing they tell you. And so if you've heard of a class that's in your list of things you have to take called differential equations, this is just kind of almost the beginning a little bit of differential equations. And here they're going to have a little bit better notation. So here they're asking us, this is problem 40 out of your book, find the solution of the following initial value problem. And so what we're looking at doing is they're asking us to find the antiderivative of this and find the antiderivative of this and use this particular solution to find the value C. And then we're going to find, in the end, we're going to find F is what we're going to be finding. And so we'll use this because F here, right, had a C in it. Okay, so a little bit better notation here. I mean, that was a little bit awkward notation that when we say that when we take the antiderivative of something that we get the capital of it. So here they're saying, I'm going to call this F prime. And so if you take the antiderivative of F prime, what do you think you get? And yeah, you get just F. So I am going to find the antiderivative. And before I find the antiderivative, I realize that's a quotient. And my three properties that I have, erase, 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 right? And come back over here. So this is what I have to find the antiderivatives. I have these three properties here, and none of them are a quotient. Then I have these 6, but they're all trig. And so I'm like, what can I do if I want to find the antiderivative of a division? Well, the only thing I have up my sleeve right now is if I can divide it. And I'm like, oh, great. I have a binomial in the top, but a monomial in the bottom, so I can divide. So I have not found the antiderivative yet. All I'm doing is making it look like I can. Now, don't forget that the square root of x is equal to x to the 1/2. So this becomes x over x to the 1/2 plus 1 over x to the 1/2. So when you have a monomial, you can divide the pieces. And remember, the exponent here is 1, and 1 take away 1/2 is 1/2. So I haven't found the antiderivative yet, so I'm still writing the notation. And so this is x to the 1/2, coincidentally, right? So you might be saying, you get the same thing as the denominator? Yeah, it was coincidence. So then here, I'm going to get plus, I'm going to write that with negative exponents, so that's x to the negative 1/2. And I have not found the antiderivative yet, but I'm going to right now. Find the antiderivative. So when I take the antiderivative of f prime, I just get f. And it is lowercase f because they've changed the notation on me a little bit. And in fact, I like that notation better, to call the function that I'm going to take the antiderivative of f prime. I like that better. And then remember what you do. You add 1 to the exponent. So I'm over here in my thinking, right? and I'm saying to myself, this is what I'm thinking, half plus 1, which y'all agree is 3 halves. So this would be x to the 3 halves. And then remember, you're going to divide by the same darn thing, which is 3 halves. And that is the same as multiplying by 2/3. So that's how I like to do it. I don't usually write it. This is what I usually think. So over here, I'm going to have times 2/3. I barely left enough room to put that. And then on the next one, I have negative 1/2. I'm going to add 1 to it. So negative 1/2 plus 1 is half. So this is in my think, right? This is in my thinking zone. And so this is going to be plus x to the 1/2. And then you divide by the same darn thing. So you divide by 1/2, which is the same as multiplying by 2 over 1, which is 2. So I'm going to times 2 right here. And then plus a constant. And this initial value is going to allow me to find this constant, because it says when x is equal to 1, f at 1 is equal to 5. So if I come through here and I put in here f at 1, so I'm plugging in 1, so 2/3 times 1 to the 3 halves, plus 2 times 1 to the 1/2, plus the constant c, right? And then I have f at 1, but what did they say f at 1 was equal to? They said that was equal to, y'all agree? 5, right? And so f at 1, so all I did was plug in x is 1. So everywhere I saw x, I put in 1. And f at 1, well, they said it was equal to 5. And that allows me to find c, because this is going to say 5 equals, well, 2/3 times 1 to the 3 halves is 2/3. Plus 2 times 1 to the 1/2 is 2. Plus c. And see how I can take away 2/3 and take away 2 and have c? So that 5 take away 2/3, take away 2 is equal to c. I know that minus is right there. Minus. And get my calculator out, right? So here's my calculator. And so if you're thinking, I stole this calculator from someone named Kevin, you're right, I did. But I'm related to the person, so it's not quite stealing. So 5 take away 2/3, take away 2 is going to give me my c value, which is 7/3. If you use a calculator like this, then you don't have to worry about me writing always reduce and you not reducing, because this calculator reduces for you. And so 7/3 is c. Now, that's not my answer. That's not what they wanted for the answer at all. What they wanted for the answer is this. F at x equals, well, what did f at x equal? And we're going to go find it right here. It equaled 2/3 x to the 3 halves, because x can take on infinitely many values, not just 1, but it can take on 2 or 7 or 18 or 57 or whatever, plus 2x to the 1/2 plus, but we use the initial value that when f was 1, that when x was 1, that the function was equal to 5, right? And we found, and that allowed us to find out what c was. So instead of saying plus c here, we used our initial value to find the value of c. So this is plus 7/3. And then this is the answer that they were looking for as the final answer. So that if I was to put in 1 for x and did the arithmetic, this side over here should equal 5 is what it should equal. And if I take the derivative of this, take the derivative of that, 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 it ought to equal that right there. Which would take me a little bit to manipulate it back into that form, but I definitely can check that it does. I haven't really left myself enough room to check those two things, and so I wish I had left myself enough room. I got one wrinkled piece of paper and some paper that I've been drawing on. which I'd be too embarrassed for anyone to see. So, so I'm getting here, I don't know, I'll put it right here. Maybe I can fit it right here. So down here below, and I'm going to just check that it worked. So I have to check two things. I have to check that f at 1 equals 5. So go right here and put in 1. So f at 1 would equal 2/3 times 1 to the 3/2 plus 2 times 1 to the 1/2 plus 7/3, right? And then I could take this calculator right here that I stole, didn't really steal, borrowed from a family member. 1 raised to the 3/2. I could get crazy and put it in my calculator, the whole thing. You're like, I know that 1 to the 3/2 is 1. Don't put that in your calculator. Plus 2, and then this is raised to the half. And you might be saying, yeah, I know that's 1. Don't put that in your calculator. Okay, I won't. Plus 5/3. No, you're like, oh, you already put it in there. Plus 7/3. Sorry, I said 5/3, but I really meant 7/3. And I'm expecting that I will get 5. And if I don't get 5, then I know I've made a mistake. And so I do get 5. So check. So this is one thing I have to check if I want to make sure that it worked. And the other thing I have to check, and I'm going to write it up here. So this is in the check zone. This is my answer. My answer. This is what would go on my answer line, right? And all I am doing is checking, and I have two things to check. Check 1 and check 2. And the second thing I need to check is that when I find the derivative of it, it equals this, right? And so that's the next thing I'm going to check. So I'm going to find the derivative right here. So this 2/3 holds still times 3/2. And then you take away 1 from the exponent. 3/2 take away 1 is 1/2. Plus the 2 holds still. You take away 1 from the exponent. So that's negative 1/2. And I didn't move the half down in front. Why didn't I move the half down in front? I don't know. So times the half comes down in front, and then you take away 1 from the exponent. So 1/2 take away 1 is negative half. And then the derivative of a constant is 0. So that's 0. Now you might be looking at that and saying, well, that doesn't equal what you started with up there. And you notice the 2 and the 3's cancel. And so this thing right here is equal to x to the 1/2. The 2's cancel here, plus x to the negative 1/2. And I'm hoping that you're noticing that, hey, that's this right here, right? And so could I go backwards and get to that? And the answer is certainly I could, right? Definitely. I think I probably would be too lazy to do that on a normal. But today, I'm feeling so unlazy. But this would be 1 over x to the 1/2. Is that okay? And then I would get a common denominator right here, right? Because I'm going to put them together in one fraction. And I would be multiplying by x to the 1/2 top and bottom. I'm going to squeeze it in. So x to the 1/2 times x to the 1/2 is x to the 1 over 1 times the square root of x. So that's x, the square root of x. I'm going to write, instead of x to the 1/2, I'm going to write the square root of x. And then plus 1 over the square root of x. Now they have the same denominator. And so I can add the numerators together, x plus 1 over the square root of x. And you notice this is exactly what I started with. So I went all the way back to the beginning. So those are the two things to check to make sure that you've done it right. That when you plug in your initial value into this, that I have a box around, and I've tried to really say, hey, this is my answer, that it's true, and it was. And also that when you find the derivative of it, it is what they said it was going to be, and it is. So hot diggity dog on that. Okay, we have just a few more to do, not that many, just 2. And so this is problem 62, and we're doing a good job. And it says, find the solution of the following initial value problem. And they've given us a at t. And you might not recognize a at t and remember that it is acceleration. But maybe they even had in the directions that don't forget A is up, and I didn't type them up, that A is acceleration, because this is what I put over here. Just to remind you, remember that when you take the derivative of, if you take the derivative of S, you get velocity. And if you take the second derivative of S, you get the derivative of the velocity, which is equal to acceleration. So acceleration is the second derivative of S. So now what they're wanting me to do is they're wanting me to go backwards, right? And so these are actually set up to find the antiderivative. And so I can go and I can look. These here, both of them, when I go back to find and I wrote it on the inside of your booklet right here too, just so that when you're finding your trig ones, if you can't find that you can find it really carefully. This is the finding the antiderivative of sine. It's equal to negative cosine. In this case here, see how this one doesn't have a coefficient in front of the t? So the a, if you will, right, is 1, is what it is. And so they said here that sine of, and they said x, but t is, we can change the variable if you like. They said the antiderivative, would be negative cosine. My a is 1, and because I don't have a coefficient of t, is what that would be, plus a constant, right? And so just kind of looking, just making sure that I'm putting in a is 1 right here, and I'm just writing it down. I'm putting in a is 1 here, and so a is 1, so divided by 1, so negative cosine of x. And then the antiderivative, if you have cosine of, my a is 1 as well on that one. So if you have cosine, if you take the antiderivative, it's positive sine. Okay, so I'm going to write that up here. So cosine of t, and if I found the antiderivative of it, it would be sine of t, because the a's would be 1. So divided by 1, and the coefficient would be 1. So now we're gonna give a whirl to this. If I find the antiderivative, find the antiderivative So if I find the antiderivative of acceleration, I ought to get back to, can you think what it would be? I ought to get back to velocity is what I ought to get back to. So when I find the antiderivative of acceleration, I ought to get back to velocity. So this will be velocity. The 3 holds still. And then I find the antiderivative of cosine of t, which I've already told you is sine of t, minus 2 times, and then I'm on finding the antiderivative of sine of t, and the antiderivative is negative cosine of t, so times, and I put parentheses in there because it was negative, and then plus a constant. And then I just want to clean that up just a tiny bit because I didn't fix the sign. So this is 3 sine of t plus 2 cosine of t plus c. And they told me when t is 0, v at 0 equals 4. So if you were to come in here and put in 0 for t, v at 0 equals 3 times sine of 0 plus 2 times cosine of 0 plus c. And what they said that v at 0 was equal to right here is 4, right? So they said this was equal to 4. And sine of 0 is 0. So this is 3 times 0. Cosine of 0 is 1. So plus 2 times 1 plus c. So this is gone. And so if I'm trying to find out what c is, I got 4 equals 2 plus c, right? So c equals 2. And so then I can put this together, right? V at t. So I'll say therefore, or thus, or whatever you want to say. Right here, no, the one where I cleaned it up, right here, equals 3 sine of t plus 2 cosine of t, but the constant was 2. So I used that initial value to find the constant 2. And now I have the velocity function. So there's the velocity function. Now it was asking me to go back and find s. So I can find the antiderivative again. So do it again. Find the antiderivative. So the antiderivative of the velocity is s. The 3 holds still. And the antiderivative of sine of t is negative cosine of t. The 2 holds still. And the antiderivative of cosine of t is sine of t. And the antiderivative of 2 is 2t. It's easy to say 2x, but the variable we're using is t. So 2t plus a constant. And your book calls the constant, since we have, it's not going to, it might be 2, but it might not be 2. So they don't call it C again. They actually call them, I think in the book, if I'm not mistaken, C1 and C2. The book I learned out of called them C, and then if you had another one coming along, they called it D, and the same problem. So I'm going to call it D. It doesn't matter. You name it whatever you want. I guess the reason that you wouldn't want to call it D is that D does look like a 0 over there. And so maybe I'll make it a fancy D. How's that? Now it doesn't look like a 0. D. I'm going to find that constant D. Okay, so I'm going to clean this up and make a note to myself that maybe you needed more room if you're going to write so many steps. Yeah, you get where you can kind of skip a few of these steps probably. Oh, the fancy D. Okay, now we're going to go find the fancy D. They had told us that s at 0 equals 0 is what they had told us. So what we're going to do is we're going to put right in here for t, we're going to put in 0. So that's minus 3 times cosine of 0 plus 2 times sine of 0 plus 2 times 0 plus the fancy D. And they said that this s at 0, right? S at 0 is equal to 0. So right where I see s at 0 right there, I'm going to put 0 equals cosine of 0 is 1, so minus 3. Sine of 0 is 0, so that's gone. Plus 2 times 0, that's gone. Plus the fancy D. And so the fancy D is equal to 3. Thus, and this is going to be our final answer, thus. And the final answer is going to be right here where I cleaned it up just a tiny bit, right here. S at t, because t is not always 0, minus 3 times the cosine of t, plus 2 times the sine of t. I just used the initial condition, plus 2 times t, plus d, and I found the initial condition to find the d, plus 3. And this is differential equations, right? Some basic differential equations, and you'll learn more about differential equations when you take Math 6D, if you have to take Math 6D. Anyway, we did a lovely job on that. It was beautiful. One more problem, and it's a word one. And then we'll be done. And so it says motion with gravity. And it says, consider the following description of a vertical motion of an object subject only to acceleration due to gravity. Begin with acceleration, the acceleration equation. A at t equals, that's gravity, negative 9.8 meters per second squared. So it says a stone is dropped from the upper observation deck of the space deck of the CN Tower, 450 meters above the ground. Find the velocity of the object for all relative time. And I said this was before A, because what they asked you to answer was these questions. But in order to answer those questions, what you need to do is you need to find the velocity equation is what you need to do. And it's really helpful. So that's why I called it before A, because this is really the first question that they asked here. And so if you take the antiderivative of acceleration, then you get velocity. And that's what it's asking me to find here. And if I take the antiderivative of a constant, this would be negative 9.8t. plus a constant c. And so what they're telling us is that they're on, I'm going to draw a picture. They have this big building. So this is the building. And they have, can't see my building. That's my big building. Here's some windows in my big building. Lots of windows. This building is really tall. And you got a person up here, and this person has their hand and they have a stone in it. And they're going to drop that stone, and that stone's going to go straight down and hit the sidewalk. And they've cleared the sidewalk, so it's not going to hit anybody or anything like that. I know that's a really good picture of a stone being dropped. That's just a hand reaching over is all that it is. Because anyone standing up would get dizzy and fall over with a stone. So we don't want that to happen. And so there they are, just dropping the stone, and it just goes straight down. So at time 0, so I'm going to write this. At time equals 0, would you agree with me that the velocity of the stone, if I'm holding the stone, just like I'm holding this eraser in my hand, so here's the eraser being held in my hand, and I'm going to drop it onto my table, but at time 0, the velocity of that eraser right here, before I drop it, and they're going to say go, and I'm going to drop it, and right at that instance, as they say go, the velocity of that eraser is 0, right? So at time 0, the velocity of the stone is 0. And I'm going to use that initial condition to find the constant c. So when you put in v at 0, negative 9.8 t 0 plus c. So I get v at 0 was 0. I get 0 equals 0 plus c. So c equals 0. And if I forgot to do that, I would have got away with it on this one. And so that my velocity equation is this. Now, that would be different if instead of dropping the stone, they were throwing the stone. And if they were throwing the stone downward, because it would be going downward and the velocity going down is negative, then whatever they told you that the rate that they could throw the stone at would be negative. And so we would have had here the velocity would be a negative value. So just because I'm dropping it 0, if I was to take the stone and I was to throw the stone upward instead of just dropping it, if I was to throw it upward, then since it would be going upward, the velocity would be positive. And then the stone would have to go up, and then it would come back down. And so anyway, so that's what would be happening there. So then it said, but in this case, the stone was just simply dropped. So the stone was dropped without any force going down or force going up. And so find the distance of the stone above the ground. Find the distance of the stone above ground level at time t. So they're asking us to find s, because that's what s represented was the distance. So all we have to do to find s is find the antiderivative of this. So the antiderivative of v is s. The antiderivative of this is the negative 9.8 holds still. You add 1 to the exponent, which is 2, and divide by that 2. So divide by 2, right? And then plus a constant. And I've already used c, and so I use d. Your book would say we already use c, so we'll use c1, or they might even call it c1 and c2. And so, but just so that no one, you could call it c again if you wanted, but just so that no one gets confused that it's going to be 0 again. It's actually not going to be 0 again, I think. And so at time 0, so the stone is up here at the top of the building, right here, and the time is 0, and the velocity of the stone is 0, because we're just going to drop it. And I'll ask you this question: how high is the stone off the ground? Well, it's the same height as the building, and they said the building was 450 meters, right? So the s is equal to 450 meters. So I know that when time is 0, the velocity is 0, and s is 450 meters. So when you plug in here, I guess I could have divided that first. 9.8 divided by 2 is 4.9. And so this is s at t equals negative 4.9 t squared plus d. And now I'm putting in 0. And so when I put in 0 plus d, now remember what s at 0 was equal to. S at 0, when t is 0, s is equal to 450. So this is 450 equals, that's 0, equals d. So d is 450. So they asked me to find the distance of the stone at above ground level at time t. And so I have s at t equals, right here, 4.9, negative 4.9 t squared plus 450, because that's what I just found d was, right? So I'm putting it right back in this equation where I cleaned it up, but I found d is 450. So if the stone has been falling 1 second, I can put in the time is 1 second, and I can find out how high above the ground the stone is. If the stone has been falling, 1.5 seconds, I'm not wanting it to get very, very many seconds, because at a certain point the stone hits the ground, right? And it doesn't go any further than that. And then this equation doesn't talk about the stone anymore. But this would tell find the distance of the stone above the ground at all. This would be how many meters the stone is above the ground at all times. How long does it take the stone to reach the ground? So that's the next question they ask. How long is time? So this is another way of saying how long is find t. So that's what they're asking me to find. And they want to know when the stone reaches the ground. So if we kind of look here at the stone reaching the ground on my picture. So here's my stone reaching the ground. The time is unknown. The velocity actually is unknown as well. The instant it hits the ground there, the velocity is some negative value, but it's not known. And s, when it hits the ground right there, so this is, the arrow is going there to this place where it's hitting the ground. So I know that I've kind of written uphill there, but I didn't mean to. But s, right at that spot, is how many feet the stone is off the ground. And s is equal to 0. Do you agree? So if the stone's on the ground, s is equal to 0. So if I look at the equations that I have boxes around that I found, if I use this equation, I need to know the velocity, which I don't know. If I use this equation, I need to know the time, which I don't know. So not a helpful equation for what I have going right now. If I use this equation right now, this one right here, it has s in it, which I know is 0, and has t in it, which I would like to find. So hot diggity dog. So that's what I'm going to do. So I'm going to use that equation right there, and I'm going to set s at t to equal 0. I'm going to be setting s to equal 0. So this is going to look like negative 4.9 t squared plus 450 equals 0. And when I solve this, I'm going to find how long it takes the stone to go from the top all the way to the bottom. I would probably add the 4.9 t squared to the other side of the equation to make it positive, and then divide by 4.9. So divide by 4.9. So that I get, and I'm going to put this in this calculator right here, 450. Oh man, I haven't had enough tea today. I have a little bit of headache. And I'm getting 4,500 divided by 49. Equals t squared. And I want to solve for t. And so I can just take the square root of both sides. So t, so here, it's this property that we learned in my algebra class. We call it this: x squared equals a number. In this case, I have t squared instead of x squared. And we say if this is true, then x equals plus or minus the square root of that number. And they call that the even root property in our textbook, or the square root property in our algebra textbook. So that's what I basically have going here, right? Instead, I have t. So this would say that t, this is my if, then t would equal plus or minus the square root of 4,500 over 49. And I hope that you're saying, well, time's not negative, so that's the reason I don't need the plus or minus. And people ask me, should I simplify that? Yes. And if you don't know how to simplify that, go get a calculator that does know how. That's my recommendation. So I'm just putting that in my calculator just like I see it, because yes, I'm a math person. I should simplify that. And so this simplifies to be 30 square roots of 5 over 7 seconds. And this is the exact value, which us math people really love to talk about the exact value. That's how we are. We like to. So that's how long it takes. But we also like approximations as well. So I'm going to go ahead and do an approximation here by hitting S to D. And so I always make sure that people know the exact value when I'm in a math class for certain. And so in this case, wow, wouldn't have expected it to take 9.5 seconds or 9.6 seconds. And so 9.6 seconds, it didn't tell me where to round here. Probably it didn't tell me where to round because probably in the back of the book they have that answer, the exact answer. Then it asks, what velocity does it strike the ground? Well, remember when it was hitting the ground, the time we just found, it was 30 square roots of 5 over 7. I don't have room to write that there. The velocity was unknown and S was 0. And so now we're going to find that velocity, but I did tell you it's some negative value when it's whacking the ground there. Okay, and so how am I going to find the velocity when it's striking the ground? Well, I know that t is equal to 30 square roots of 5 over 7 when it hits the ground, right? And so I'm going to put that value right in here for the velocity. So the velocity at 30 square roots of 5 over 7 equals negative 9.8 times 30 square roots of 5 over 7. Us math people, we run around with the square root of 5 thinking it's fine. Okay, so here we have negative 9.8 times, and then it's a fraction, 30, I could have put parentheses too, square roots of 5, but I put the times sign instead, divided by 7. And the calculator says that's negative 42 square roots of 5, which I was really grateful that it would give me the exact value. And I said to it, boy, that's really nice of you. And this is the velocity, right, at, I'm going to say on ground, the velocity when it's on the ground, right, when it just strikes the ground. I guess I should have put just strikes the ground. And now it should be in meters per second is what the unit should be on that. And so the velocity as it just strikes the ground, is roughly, I'm going to push S to D, negative 93.9 meters per second. And so this is the exact value. This is an approximate value, right? And we're math people. And so we like to give both for certain on things that would make sense to kind of know. If they asked me to turn that into miles per hour, then I would need to know how to convert meters to miles. And I might need to know how to convert meters to kilometers and then kilometers to miles. And you'll see a problem like that if you go do the homework. Okay, so that's the story on that. And I think that's my video. And how many minutes did it take me? 1 hour and 8 minutes. I knew it was going to be just slightly over an hour. Okay, watch it in several shots. Oh, you've already watched it. No more hints. Okay, bye-bye.